What if the universe is not made of matter, but of connections? Imagine peeling back everything you see, the stars, the planets, the swirling clouds of gas, even the atoms that make up your own body, and finding that beneath it all lies not solid substance, but invisible relationships. Something deeper than particles or waves, something that ties one event to another across the emptiness of space. In the early days of physics, when light was still being argued over as a wave or a particle, no one could have imagined that nature might be built from something even more abstract. Yet, as scientists probed the quantum world, they found something unsettling. They found that particles could be separated by great distances and still remain mysteriously linked. When one was measured, the other seemed to respond instantly, as though space itself carried no meaning to their relationship. Albert Einstein called it spooky action at a distance. To him, it violated every instinct about how reality should behave. If nothing can travel faster than light, how could one particle possibly know what happened to another light years away? This strange phenomenon became known as quantum entanglement. It is one of the most verified, yet least intuitive features of quantum mechanics. Entanglement means that two or more particles share a single quantum state. Their properties are not independent. They are part of one combined reality, even if separated by immense distances. Measure the spin of one, and you instantly determine the spin of the other. It is not that a signal passes between them, but that they were never truly separate in the first place. Physicists tested this idea rigorously, and the results left no doubt. In the 1970s, John Bell designed an experiment that could expose whether hidden variables might explain the connection. But time and again, nature sided with entanglement. Experiments by Alain Aspect in the 1980s and many others since have confirmed that quantum correlations truly defy classical logic. The universe, it seems, does not consist of isolated pieces. It is an interconnected whole. When we look around, we see distance as separation. Yet entanglement whispers that separation might be an illusion, that the fabric of reality is woven from relationships rather than things. Even the emptiest region of space is not truly empty. It hums with invisible connections, like a vast cosmic web that binds everything into one coherent system. If this web were to vanish, what would be left? Could there still be a concept of space, or would the entire structure of the universe dissolve into nothingness? Quantum entanglement has become more than a curiosity. It is now seen as the most fundamental aspect of the quantum world. Every field, every particle, every photon of light participates in this invisible dance of correlation. It is the ultimate glue of reality, and yet it is invisible. Not a force we can touch or measure directly, but something revealed only through patterns and probabilities. To understand how profound this is, imagine a pair of dice that always show numbers adding up to 7, no matter how far apart they are. Roll one on Earth and the other on Mars, and if the first lands on 2, the second will show 5. It is as if the dice share a secret code that transcends distance. But entangled particles go even further. They share uncertainty. Before measurement, their outcomes are not merely unknown, they do not even exist as definite numbers. The results come into being only when observed, and somehow the two outcomes remain perfectly coordinated. Reality, it seems, waits for observation to decide, yet it maintains its mysterious unity. Some physicists began to wonder whether these invisible threads could do more than connect particles. Could they be the very scaffolding that gives rise to space itself? Could the geometry of the universe, the smooth, continuous fabric described by Einstein, emerge from networks of quantum entanglement at the smallest scales? This idea changes everything. It suggests that space-time, gravity, and perhaps even causality are not fundamental, but emergent. That what we experience as geometry is just the large-scale pattern of underlying quantum relationships. The curve of space-time might be nothing more than the way information flows through this network of entanglement. If this is true, then reality is not built from stuff, but from connection. the sun, the planets, and the atoms in your hand might all be expressions of a deeper unity, a cosmic conversation of information. Every corner of the universe participates in the same dialogue, and gravity itself could be the way that dialogue organizes the flow of information. We are used to thinking of space as a stage and matter as the actors. But what if the stage is woven from the same threads that tie the actors together? What if space exists only because particles are entangled, because relationships create the sense of distance? Remove those relationships, and the play ends. The stage, the actors, even the concept of location itself would fade away. The deeper scientists look, the less they find a solid boundary between things. Reality behaves as if it were one giant quantum system, fragmented only by our limited perspective. What we call objects are just clusters of highly entangled information, stable patterns floating in an ocean of correlations. We see separation because we can only perceive a small portion of the network at once. The rest, the unseen entanglement, is the true substance of the cosmos. Einstein might not have liked it, but quantum mechanics leaves little room for a purely local world. The evidence suggests that the universe is globally connected in ways that defy classical intuition. And while this does not allow for faster-than-light communication, it does hint at something even more astonishing: that the speed of light may itself arise from the structure of those connections, a built-in limit to how information can flow through the cosmic web. If matter is not fundamental, if space and time themselves are born from entanglement, then the question becomes, what is entanglement made of? Or is that the wrong question entirely? Perhaps entanglement is not made of anything. Perhaps it is everything, the invisible architecture from which all phenomena emerge. This is where the boundaries of physics blur into philosophy. What we perceive as reality may be a projection of deeper informational relationships. Particles, fields, and even geometry could be shadows of something more abstract, the pure pattern of correlations that define existence. The challenge, then, is to understand how these invisible threads give rise to the tangible world. How can simple quantum connections produce the rich dynamic structure of space-time and the familiar pull of gravity? To answer that, we must follow the trail from Einstein's geometry to the strange new frontier, where information itself becomes the building block of reality. The universe may not be a collection of objects in space. It may be a vast, self-knitting tapestry of quantum information, an endless conversation where every particle, every star, and every thought is a note in a cosmic symphony. Gravity, time, and motion may be the rhythm of that song, the visible echo of invisible threads connecting all that exists. In the silence between stars, the universe whispers through connection. What we call emptiness is alive with subtle entanglement, a web of invisible bonds stretching across the vastness of space. When physicists peer deep into the quantum world, they do not find solitude, but relationship. Every particle, even the smallest flicker of energy, is defined not by what it is alone, but by how it is linked to the rest of the cosmos. This realization did not come easily. For decades after Einstein's protest, many dismissed entanglement as a strange mathematical curiosity. They treated it as a feature of theory, not a property of nature. But when experiment after experiment confirmed its reality, it forced a shift in how we see the universe. Entanglement is not an exception, it is the rule. Every corner of the quantum world participates in this connectedness, and the strength of those connections determines what kind of reality we perceive. Consider what happens when two particles become entangled. They start as one shared state, inseparable and perfectly correlated. Separate them by a laboratory, by a planet, or by a galaxy, and that shared state persists. It does not weaken with distance, for distance is irrelevant to entanglement. It lives in the abstract space of information, not the physical space we move through. When we measure one particle, we collapse the entire relationship, not just a local value. That collapse seems instantaneous, but it is not a message or a signal. It is a revelation of something that was already true. 2. Parts of one whole, expressed through the illusion of space. To imagine this, think of a coin spinning through the air. Before it lands, it is not heads or tails, it is both, a superposition of possibilities. Now imagine two such coins, entangled, so that when one lands on heads, the other must be tails. They do not decide this through communication. It is written into their shared quantum state from the start. The act of observing one does not change the other. It merely completes a story that was always collective. This subtle difference matters deeply, for it hints that information might be more fundamental than space itself. Entanglement ties together quantum states in a way that cannot be described by local geometry alone. And when we try to separate the world into pieces, to assign independent properties to each region of space, we find that we cannot. The quantum fields overlap, the wave functions intertwine. Space resists being divided cleanly, as if its continuity depends on entanglement remaining intact. In recent years, theoretical physicists have begun to ask a daring question. Could the geometry of space-time itself be built from these quantum connections? The suggestion first appeared not in the language of philosophy, but in the precise mathematics of holography. In certain models of the universe, known as anti-de Sitter spaces, gravity and geometry in a three-dimensional region can be described entirely by quantum information living on its two-dimensional boundary. This is the ADS-CFT correspondence, one of the most profound insights in modern theoretical physics. It suggests that what happens inside a volume of space can be fully encoded by information on its surface, much like a hologram storing a three-dimensional image in 2 dimensions. When scientists explored how this holographic principle works, they found that the amount of entanglement in the boundary theory directly determines the shape of the interior space. Increase the entanglement, and the geometry smooths out, expanding like a balloon. Reduce it, and the space pinches, forming narrow throats, or even disconnecting entirely. In this picture, space-time is not a static backdrop, but a living network whose structure flows from the pattern of quantum correlations. The geometry is literally the map of entanglement. This connection between information and geometry is not just poetic, it has been calculated, tested, and simulated in models. The equations that describe gravitational curvature can be derived from the equations of entanglement entropy. This means that what we feel as gravity might be the macroscopic reflection of microscopic information flow. When entanglement changes, the geometry adjusts, bending space in ways that Einstein's theory perfectly describes. The remarkable implication is that gravity may not be a force at all. It might be an emergent phenomenon, born from the statistical behavior of countless quantum links striving to balance their information. Where there is more entanglement, space stretches. Where there is less, it contracts. Planets, stars, and black holes are regions where entanglement density shifts dramatically, shaping the curvature we perceive as gravity's pull. In this new view, the universe becomes something like a woven tapestry of relationships. Each thread represents a line of entanglement, and together they create the geometry we inhabit. Ripples through this fabric are gravitational waves, changes in the entanglement pattern that propagate through the network. The familiar space-time continuum of relativity becomes an approximation, a large-scale pattern emerging from the quantum-level code that underlies everything. If we could peer down into the deepest layers of reality, perhaps we would not see particles or waves at all, but a vast network of nodes and links, each node a quantum state, each link an entangled bond. Space itself would be nothing but the geometry of this network, its curvature reflecting how information flows from one node to another. This is the picture physicists like Mark van Ramsdonk and Juan Maldacena have pursued. That entanglement is not a property within spacetime, but the very mechanism that creates spacetime. It is a radical thought, yet it resolves deep paradoxes. The mystery of why gravity and quantum mechanics have resisted unification may stem from the assumption that space is fundamental. If space is instead emergent, then the conflict disappears. Quantum mechanics no longer has to fit inside geometry. Geometry arises from quantum mechanics. The fabric Einstein described is not the stage, but the play itself, the visible outcome of invisible quantum relationships. There is something profoundly human about this realization. For centuries, we have sought the smallest pieces of reality, dividing matter again and again, searching for ultimate building blocks. But the universe seems to whisper a different truth. The more deeply we look, the less we find isolated pieces, and the more we find connection. The fundamental essence of existence might not be substance, but relationship. The cosmos holds together not through particles colliding, but through patterns of information binding all things into one. The invisible threads of reality are not metaphors. They are measurable, mathematical, and astonishingly real. They may stretch beyond our ability to perceive, linking stars, black holes, and even the birth of time itself in a single cosmic network. If the universe is indeed made of connections, then gravity, space, and time are simply the visible shadows of that unseen web, a tapestry of entanglement weaving the story of everything. From the moment we open our eyes and look up at the night sky, space feels like the most fundamental thing there is. It seems silent, smooth, infinite, the stage upon which all matter moves. But if quantum physics has taught us anything, it is that what appears simple hides infinite complexity. What we call empty space is not empty at all. It is seething with invisible activity, restless with quantum fluctuations, and alive with entanglement that ties every region of the universe to every other. In the vacuum of space, pairs of virtual particles appear and disappear in moments too brief to measure. These tiny fluctuations are not random noise. They are part of a grand, connected structure. Every fluctuation, every bit of uncertainty, is entangled with the rest. The quantum vacuum is not a void, but a vast sea of relationships. The deeper we look, the clearer it becomes that emptiness is the greatest illusion of all. Imagine that space itself were to lose all entanglement. What would remain? Theoretical studies have explored this question, and the result is startling. Without entanglement, the equations describing quantum fields fall apart. The structure of space-time dissolves, and the universe becomes a disconnected collection of meaningless points. Entanglement is the thread that holds the fabric together. Remove it, and the very concept of geometry ceases to exist. This discovery was first glimpsed in the study of black holes. When physicists Jacob Bekenstein and Stephen Hawking examined black holes in the 1970s, they found that the amount of information a black hole could contain was not proportional to its volume, but to its surface area. This simple observation changed everything. It suggested that information, and therefore entropy, scales with area, not volume. That meant the true degrees of freedom of the universe might live not inside space, but on its boundaries. The holographic principle was born. According to the holographic view, all the information needed to describe a three-dimensional region of space is encoded on its two-dimensional boundary. The inside is a projection of that boundary data, just as a hologram produces a three-dimensional image from a flat surface. This idea seemed impossible at first, but it fit perfectly with the behavior of black holes, where the surface area measures the total entropy, or information content, of everything that falls within. In this picture, space and gravity inside the region are not fundamental. They emerge from the information encoded on the surface. If this principle applies not only to black holes but to the universe itself, then everything we experience might be a holographic projection. Our three-dimensional world could be the shadow of quantum information written on a distant boundary beyond our perception. The distances, the geometry, and the forces we feel would be nothing more than manifestations of how that information is organized. Entanglement, again, plays the central role. It is the pattern of connections in that boundary information that determines the shape of the space we live in. This idea was given precise mathematical form in the anti-de Sitter and conformal field theory correspondence. In this framework, the geometry of a gravitational universe, complete with curvature, black holes, and time, can be described by a quantum system without gravity living on its boundary. The strength and distribution of entanglement in that boundary system literally create the geometry of the interior. In this way, the cosmos becomes a map drawn by quantum information itself. It is difficult to grasp because our senses evolved to see the macroscopic world, not the quantum code beneath it, but the evidence continues to build. Quantum simulations, tensor network models, and holographic entropy calculations all point to the same truth. Geometry is information, and information is entanglement. This also reshapes our understanding of Einstein's legacy. His theory of general relativity showed that gravity is not a force, but the curvature of space-time caused by energy and mass. Now, quantum theory hints that curvature itself is the effect of information flow. Where there is more entanglement, space-time expands. Where it decreases, it contracts. The bending of light around a star, the motion of planets, even the stretching of space-time by a gravitational wave could all be manifestations of entanglement redistributing itself to maintain equilibrium. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. Yet the deeper we dive, the more the universe seems to speak the language of information. Each physical law, from the orbit of a planet to the decay of a particle, may simply describe how information arranges and evolves within the cosmic web. The flow of entanglement defines what we perceive as motion, interaction, and force. Perhaps this is why the speed of light is constant. It is not a property of photons alone, but a feature of the information structure that underlies all space. It is the universal limit on how correlations can reorganize through the quantum network that makes up spacetime. Light does not merely travel through the universe, it traces the rules of the universe's informational geometry. When seen this way, even time takes on a new meaning. Time might not be a flowing river, but the unfolding of informational change. The arrow of time could emerge from the natural tendency of entanglement to spread, to grow, to maximize. The universe evolves as information flows outward, forming ever more complex structures. Atoms, stars, galaxies, and consciousness itself, all built upon the same invisible quantum foundation. In this vision, everything we experience, matter, energy, space, and time, is the expression of one unified principle, the dynamic network of quantum relationships that underlie reality. We are not observers standing outside this network. We are part of it. Every thought, every breath, every photon that touches our skin participates in the same entangled web that shapes the cosmos. When you look at the night sky, what you are truly seeing is not emptiness dotted with stars, but the luminous pattern of connection itself, the living geometry of information stretching across eternity. Gravity, that ancient mystery that once seemed like a pull between masses, may be nothing more than the visible whisper of those invisible threads tightening and relaxing, shaping the dance of galaxies and the flow of time. And so the question remains, if the universe is made of connections, who or what set them in motion? Perhaps there was never a beginning, only the continual weaving of entanglement itself, a timeless conversation that gives birth to everything that is and everything that will be. The next step in this journey is to understand how Einstein's smooth, continuous spacetime emerges from the discrete, probabilistic realm of quantum information. To do that, we must explore the geometry of gravity itself, the way space bends, twists, and curves as a direct reflection of the hidden web beneath. Only then can we begin to see how the invisible threads of reality give rise to the fabric of existence. Gravity was once the simplest of all mysteries. An apple falls, the moon orbits, and the planets trace elegant ellipses around the sun. For centuries, we thought of it as an invisible pull, a force reaching through the emptiness between objects. Isaac Newton described it beautifully, but even he admitted he did not know what it was. He could measure its strength, predict its motion, but not its cause. What invisible hand reached across space to draw one mass toward another? It would take 200 years before that question began to find a deeper answer. When Albert Einstein reimagined gravity in his theory of general relativity, he replaced the notion of an invisible force with something more profound. Space and time, he said, are not static or empty. They are part of a single dynamic fabric that bends and stretches under the influence of mass and energy. The sun does not pull the planets, it shapes the geometry around them. The planets follow the straightest possible paths in that curved geometry, and those paths appear to us as orbits. This vision was revolutionary because it changed the meaning of motion itself. What we once thought of as attraction is simply geometry. Space tells matter how to move, and matter tells space how to curve. That single sentence captures the essence of Einstein's cosmos. It is elegant, complete, and breathtakingly beautiful. Yet, beneath its perfection lies a profound question. Why does the universe have a fabric at all? What gives rise to this geometry that bends and flexes? To Einstein, space and time were smooth and continuous. The curvature of space-time could be described by equations that relate energy and momentum to geometry. These equations are known as the Einstein field equations, and they form one of the most successful theories in all of science. They predict the bending of light by gravity, the time dilation near massive bodies, and even the existence of black holes. Every observation has confirmed their accuracy. Yet, the theory assumes that space-time is a continuum, an infinitely divisible sheet that can bend but never tear. Quantum mechanics, however, tells a different story. In the quantum world, nothing is continuous. Energy comes in discrete packets, or quanta. The position of a particle is not fixed until measured, and the vacuum itself flickers with uncertainty. If we zoom in far enough on the smooth fabric of space-time, we would not find a continuous surface, but something more like foam, ever-changing, unpredictable, and woven from probabilities. At distances smaller than the Planck length, about 1/10 million trillion trillionth of a meter, the concept of smooth geometry breaks down entirely. Space-time may dissolve into something more fundamental, something built not from points, but from information. This is where the language of relativity and the language of quantum mechanics begin to clash. Relativity describes geometry, continuous and deterministic. Quantum physics describes probability, discontinuous and uncertain. For over a century, physicists have tried to reconcile these two views, to write a single theory that can describe both the curvature of galaxies and the jitter of atoms. Yet every attempt encounters the same barrier. The smoothness of space-time cannot survive the granularity of quantum theory. Perhaps the problem lies not in the mathematics, but in our assumptions. We have assumed that space-time exists first, and that matter and energy move within it. But what if space-time itself is not fundamental? What if it emerges from something deeper, something more abstract, like the invisible web of entanglement we explored before? When Einstein formulated general relativity, he did not know about quantum entanglement. He saw space-time as a real continuous field, not as an emergent structure. But now, with the insights of quantum theory, we can imagine that the geometry Einstein described is the large-scale expression of countless quantum relationships. The curvature of space-time could arise from the way entanglement is distributed across the universe. In this sense, gravity would not be a fundamental force, but a manifestation of information flow within the quantum fabric. To visualize this, picture a stretched sheet representing space. A massive object like a planet creates a depression in that sheet, and smaller objects roll toward it. That image has become the universal metaphor for gravity. But what if the sheet itself is woven from threads of entanglement? Where the threads are tightly interwoven, the fabric is smooth and stable. Where they loosen or rearrange, the geometry curves. The presence of energy and matter would then correspond to regions where entanglement patterns change, producing the curvature that Einstein's equations describe. This idea is not mere speculation. Recent studies in theoretical physics show that space-time curvature can indeed be derived from relationships between quantum information. In certain models, the equations of general relativity emerge naturally from the laws of entanglement entropy. The more entangled two regions of space are, the more connected they become geometrically. When that entanglement decreases, a gap appears, a curvature, a distortion, or even a separation of space itself. From this perspective, gravity is no longer a mysterious pull acting across distance. It is the visible effect of invisible information striving for balance. Entanglement flows through the universe like a current, and geometry bends to accommodate that flow. The shape of space, the passage of time, and the motion of planets are all consequences of how information arranges itself. To many, this sounds like philosophy, yet the mathematics supports it. The Ryutaka-Yanagi formula, developed in the context of the ADS-CFT correspondence, directly connects entanglement entropy to the area of surfaces in space-time. It shows that the geometry of a region is determined by the information shared across its boundary. The more information entangled across that boundary, the larger the area. Geometry and information are two sides of the same coin. This understanding redefines the nature of the cosmos. Space is not a container, but a network. Time is not a universal flow, but a sequence of informational changes. Gravity is not a force, but an emergent property of how the universe organizes its correlations. The laws of physics, once thought to be eternal and fixed, may themselves arise from the deeper logic of information theory. Einstein once visualized the universe as a grand, continuous fabric. But the true fabric might be a quantum one, woven not from fields or waves, but from entanglement links, threads of pure relationship forming the geometry we call space-time. The next time you stand beneath the stars and feel the gentle pull of gravity, you might remember that you are not being pulled at all. You are moving along the curves of a cosmic web, shaped by the invisible flow of quantum information connecting everything to everything else. If Einstein's theory gave us the poetry of curved space, quantum theory gives us the secret language written beneath that curve. The two seem to speak different dialects of reality. Relativity tells us that space and time form a continuous geometry that responds to energy. Quantum mechanics tells us that nature is discontinuous, granular, and governed by probabilities. The dream of modern physics has been to make these two descriptions speak as one. Yet perhaps the bridge between them has been before our eyes all along, hidden in the subtle patterns of entanglement. To appreciate this, imagine that every small patch of the universe carries within it a kind of memory, quantum information about its relationship to the rest of reality. These memories are not stored in particles or waves, but in the correlations that link them. When these links are uniform and stable, space-time appears smooth. When they change, geometry curves. In this view, gravity is not a separate force, but a natural response of information trying to equalize itself across the network of existence. Einstein's equations can be written in a way that reflects this. The curvature of space-time, expressed by the Einstein tensor, is proportional to the distribution of energy and momentum. Energy and momentum, in turn, can be seen as measures of information flow. The movement of matter is therefore not the cause of curvature, but its expression. Space curves because information moves. What we call mass might be a kind of informational density, a region where entanglement is especially concentrated. At the edges of black holes, this relationship becomes undeniable. The event horizon of a black hole is not merely a boundary in space, it is an informational surface. According to the Bekenstein-Hawking formula, the entropy of a black hole, meaning its information content, is proportional to the area of its horizon, not its volume. That single insight reveals a fundamental truth. In the universe, information is stored on surfaces, not within volumes. The geometry of those surfaces determines how information flows, and the flow of information determines how geometry behaves. This intertwining of geometry and information was made precise through the holographic principle. If every bit of information inside a region of space can be encoded on its boundary, then the interior geometry is not fundamental. It is emergent. The boundary acts like a quantum computer, processing entanglement data whose structure gives rise to the three-dimensional world we perceive. In the anti-de Sitter and conformal field theory framework, this is more than metaphor. It is exact mathematical equivalence. A two-dimensional quantum field theory without gravity on the boundary completely describes a three-dimensional universe with gravity in the bulk. In that light, the curvature Einstein described is not the bending of a pre-existing space, but the translation of entanglement patterns into geometry. The smoothness of the cosmos is an illusion, born of an unimaginably complex code. To us, planets orbit in graceful ellipses, and light follows bent paths. Beneath that elegance, the universe is computing. Every photon, every atom, every fluctuation of the vacuum contributes to the ongoing calculation that maintains the fabric of space-time. One way to picture this is to think of space-time as a vast web woven from invisible threads of correlation. Where the threads are evenly distributed, the web lies flat. Where they are denser, the web curves. A star, a planet, or a black hole is not an object sitting in space. It is a distortion of the web itself, a region where informational tension shapes the surrounding geometry. When you fall toward the Earth, you are not being pulled by an external force. You are following the natural flow lines of this entanglement geometry, like a bead sliding along a curved string. This idea also resolves one of the oldest puzzles in physics: the nature of gravitational energy. In relativity, gravity has no local energy. It cannot be bottled or extracted. That makes sense if gravity is not a force but a pattern of information. You cannot store geometry in a box because geometry is the shape of the box itself. The energy of gravity is global, not local. It resides in the relationships among regions of spacetime, not within any one of them. Another subtle clue comes from quantum field theory itself. When we divide space into two regions and measure the entanglement between them, we find that the amount of entanglement scales with the area of the boundary, not its volume. This mirrors the behavior of black hole entropy and hints that all of spacetime obeys the same holographic rule. The geometry of space is determined by how much entanglement crosses each boundary, and the flow of that entanglement determines curvature. Think of a river of information flowing through the universe. Its currents correspond to changes in entanglement, and those changes create ripples in geometry. Where information flow is strong, space curves more sharply. Where it is gentle, space appears flat. Gravity is the visible motion of this invisible river. It is not a fundamental interaction like electromagnetism or the strong nuclear force, but the statistical effect of countless microscopic adjustments in the balance of quantum information. Even time itself may be an emergent aspect of this geometry. In general relativity, time slows down near massive objects because the geometry of space-time stretches. In the quantum picture, this could reflect how information flow becomes constrained in regions of high entanglement density. The ticking of a clock measures not just motion, but the reorganization of information within the cosmic web. The slower the flow, the slower time appears to pass. In recent years, physicists have begun to simulate these ideas using quantum computers. By arranging qubits in patterns that mimic the structure of entanglement in holographic theories, they can reproduce geometric properties like curvature and even mimic gravitational effects. These experiments do not yet prove that our universe arises from such a network, but they show that the mathematics works. Geometry can indeed emerge from entanglement. If the cosmos truly operates this way, then Einstein's beautiful equations were only the surface of a deeper truth. They describe how geometry behaves, but not what geometry is. The answer may be that geometry is the shape of information itself. The universe is not a static structure filled with matter, but an evolving computation, a living web in which information flows, entanglement weaves, and gravity emerges as the large-scale whisper of their harmony. The elegance of this idea lies in its unity. Instead of two separate frameworks, relativity for the large and quantum theory for the small, we might have one. The geometry of the universe and the behavior of quantum information are two perspectives on the same underlying reality. The curvature of space is the fingerprint of entanglement, and the motion of matter is the story told by information as it seeks equilibrium. It is a story that stretches from the smallest quantum fluctuations to the vast arcs of galaxies. The same invisible logic that binds two entangled particles across a laboratory may also bind the stars across the cosmos. The geometry we inhabit is the grand reflection of that logic, the great pattern written in the language of information. Gravity is not the cause of structure, it is the consequence of connection. At the heart of every theory lies a question about what is real. When Einstein pictured space-time as a smooth, continuous fabric, he gave us a language that worked flawlessly for stars, galaxies, and even the universe itself. But when we peer into the quantum realm, that language begins to tremble. The equations no longer hold perfectly. The continuum of space-time begins to fray, and what once looked like a single seamless surface now appears grainy and uncertain. The deeper we go, the more it feels as if geometry itself is a mirage, a pattern that emerges only when enough quantum information is woven together. If this is true, then the geometry of gravity is not something given to us by nature. It is something nature builds from within itself. The universe does not start with a ready-made stage on which events unfold. The stage arises from the relationships between the events. The links of entanglement become the threads of space, and their collective structure defines curvature. Space, in other words, is not where things happen. It is what happens when things are related. This view invites us to think differently about the nature of measurement and observation. In classical physics, measuring a system reveals its state without changing it. In the quantum world, however, observation is participation. To measure a particle is to become entangled with it. The act of observation adds new connections to the web of entanglement, subtly reshaping the geometry of the underlying space. Each interaction, every exchange of information, contributes to the continual rewriting of space-time itself. We might imagine space-time as an evolving tapestry, never still, constantly updating its geometry as information flows across it. The curvature that we call gravity is the response of this tapestry to those flows. When mass gathers, the entanglement patterns around it tighten, curving the geometry inward. When energy radiates outward, the patterns loosen, flattening the geometry once more. From this viewpoint, the laws of physics are not rigid commandments, but the natural tendencies of information to organize itself efficiently across the web. This notion also reshapes how we think about singularities, the places where Einstein's equations break down, such as the centers of black holes or the first moment of the Big Bang. In classical relativity, these are points of infinite density where the geometry of space and time collapses. But if geometry is made from entanglement, then singularities are not infinities. They are simply regions where the entanglement structure fails to hold together. The quantum fabric there unravels, and the concept of space ceases to apply. The universe does not end in a singularity. Rather, space itself stops being meaningful beyond a certain scale. Quantum gravity researchers have built models that hint at this. In certain theories, the interior of a black hole can be replaced by a network of quantum states where information is never lost, but redistributed. The apparent paradox of black hole evaporation where information seems to vanish into nothingness, may be resolved if information is stored in the entanglement structure of the horizon itself. As the black hole evaporates, the information is released, encoded in subtle correlations between the outgoing radiation and the geometry that remains. Gravity, once again, acts as the translation of information flow into shape. The same principle might apply to the birth of the cosmos. At the earliest moments, before space had any size or direction, the universe could have existed as a pure quantum network. No geometry, no time, just relationships. As entanglement increased, geometry emerged. Distances, durations, and directions became meaningful only as the web grew complex enough to support them. The expansion of the universe, then, may be the unfolding of entanglement, the spreading of information across an ever-growing network of relationships. This idea blurs the line between physics and philosophy, yet it remains grounded in mathematics. Tensor network models used to study quantum systems reproduce many features of space-time geometry. In these models, nodes represent quantum states, and the links between them represent entanglement. When the pattern of links follows specific mathematical rules, the emergent structure behaves exactly like curved space-time. Even Einstein's equations arise naturally when the entanglement pattern changes in certain ways. The geometry of gravity can therefore be seen as the large-scale limit of a vast, underlying information network. The elegance of this picture lies in its unity. There is no longer a need to treat geometry, matter, and energy as separate ingredients. They are all manifestations of the same fundamental entity, information. The density of information determines curvature. The flow of information determines motion. The change in information defines time. The universe, at its core, is an informational organism, self-organizing and self-measuring. This view also explains why gravity is so weak compared to the other forces of nature. If gravity arises from the collective behavior of entanglement, then it is inherently statistical. Each individual quantum link contributes only a tiny adjustment to the overall geometry. The combined effect of countless links becomes noticeable only when vast amounts of matter are involved. That is why we feel gravity from the Earth, but not from the person standing next to us. The entanglement geometry between two small masses is simply too subtle to detect. And yet, despite its weakness, gravity is the most universal of all interactions. Every bit of energy, every particle, every quantum fluctuation participates in it. That universality makes sense if gravity is not a separate force, but a property of the entire information network itself. It affects everything because it is everything. The collective shape of the web that defines reality. Seen in this light, Einstein's geometric universe and the quantum universe of entanglement are not rivals, but partners. Relativity describes the visible pattern, while quantum theory describes the invisible code that writes it. The curvature of spacetime and the structure of entanglement are reflections of each other, like two sides of a single coin. Gravity is the macroscopic whisper of quantum connectivity. If we could somehow perceive the world not as a collection of objects in space, but as a pattern of relationships, we would see that every atom, every photon, every thought is a node in an immense living geometry. The sun's pull on the planets, the fall of an apple, even the passage of time, are expressions of this geometry adjusting itself to preserve balance among all its threads. And so, gravity is not a force that pulls. It is the shape drawn by information as it flows. The curvature of spacetime is the grand choreography of entanglement. The next step in our journey is to follow those threads more deeply, to understand how quantum entanglement does not merely shape geometry, but might actually create it. We will see how the density of entanglement determines curvature, how networks of quantum information can give rise to space itself, and how the geometry of the cosmos may be nothing more than the visible face of the invisible quantum fabric beneath. At first glance, space appears silent and still, like a calm ocean stretching without end. Yet beneath that stillness The quantum world seethes with motion. Every point in space vibrates with invisible fluctuations, an endless storm of creation and annihilation. Pairs of particles burst into existence and vanish again in time so brief that no instrument can catch them. This is not chaos. It is the breath of the quantum fabric itself. Quantum field theory teaches that space is not an empty container, but a living field of energy. Every particle, every force, every spark of light emerges as a vibration in that field. What we call matter is simply a localized excitation, a wave that momentarily rises from the sea of potential and then fades back in. But these waves are not independent. They are entangled. The quantum fabric of the universe is a network of correlations, where each vibration subtly influences the others across all of space. Entanglement is not just a property of particles, it is the defining structure of reality. When two regions of the quantum field share entanglement, they share information. Their quantum states cannot be described separately. What happens in one region affects what is possible in the other. The amount of this shared information is known as entanglement entropy. It measures how much one part of the universe knows about another, how tightly their fates are intertwined. If you divide the universe into two regions and calculate their entanglement entropy, something remarkable happens. The amount of shared information is proportional to the area of the boundary between them, not the volume of the regions themselves. This strange rule echoes the behavior of black holes, whose entropy also depends on surface area. It is as if the surface between regions holds the key to their connection, as though the boundary of space is where information truly lives. This insight changed how physicists think about geometry. In the old picture, geometry was fundamental. Distances, angles, and curvature existed first, and quantum fields lived within that geometry. But now, the evidence suggests the opposite. Geometry might arise from the pattern of entanglement among quantum fields. The smoother and stronger the entanglement, the more continuous the geometry appears. Remove that entanglement, and the fabric tears. Mark van Ramsdonk proposed this radical idea, that increasing entanglement between quantum systems pulls them closer together in the geometric sense, while reducing it pushes them apart. In his model, space-time itself is a manifestation of quantum information connecting distant degrees of freedom. Without entanglement, space disintegrates into separate, unconnected fragments. Entanglement is the stitching that holds the cosmos together. This vision reveals a startling unity. Geometry, energy, and information are not separate aspects of nature. They are the same thing, seen from different angles. The curvature of space is the way information arranges itself. The flow of energy is the movement of that information. The passage of time is the unfolding of new correlations as the quantum fabric continually rewrites itself. Imagine standing in a dark room where threads of light crisscross in all directions. Each intersection represents a quantum state, and each thread represents entanglement connecting it to others. Together, they form a glowing network. Where the threads are dense, the geometry curves inward. Where they thin, space stretches. You cannot touch the threads or see the network directly, yet it defines everything. The shape of the room, the distance between points, even the ticking of the clock. That web is the true substance of the universe, and we are part of its weave. The idea that geometry emerges from entanglement also explains why space-time is so resilient. Even though quantum fields fluctuate wildly, the overall geometry remains stable because it is built from an immense redundancy of connections. The same pattern of entanglement can be encoded in many ways, much like a digital image can survive even if some of its pixels are lost. This redundancy may be the key to understanding how space-time resists collapse and how black holes preserve information despite their apparent finality. If the universe is a quantum fabric, then every event, every motion, every thought, is a vibration within that fabric. The flow of gravity, the bending of light, even the sense of passage from one moment to the next, all arise from the collective behavior of countless entangled states. Space is not a stage where reality unfolds. It is the unfolding itself, woven from the invisible threads of correlation that bind the cosmos together. The deeper we explore this fabric, the clearer it becomes that reality is not built from matter, but from relationships. What we call particles are stable knots in the network. What we call energy is the tension along its threads. And what we call geometry is the large-scale shape that these relationships produce. The universe is not made of things. It is made of patterns, patterns of information, patterns of entanglement, patterns that think, evolve, and dream. If space-time is a quantum fabric, then the laws of physics are its stitching instructions. They describe how information flows, how entanglement evolves, and how geometry emerges from that evolution. To understand the cosmos is to understand that code, to read the hidden logic that turns pure information into stars, galaxies, and minds. But this raises an even deeper question. If entanglement creates geometry, then what creates entanglement? What mechanism drives the universe to connect, to weave itself into a coherent whole, rather than remain a chaos of isolated quantum bits? Perhaps the answer lies in the nature of information itself, that information seeks completeness, that correlations grow naturally because they minimize uncertainty. The cosmos might be the ultimate, self-organizing system, forever weaving new connections to reduce its own ignorance. From this perspective, the quantum fabric is not just the structure of the universe, it is its story. Every event adds a new thread to the tapestry. Every observation rewrites a small part of it. Every interaction echoes through the web, changing the geometry in ways both subtle and grand. The universe is not a static object, but a living narrative, told through the language of entanglement. The next step in this story takes us beyond geometry and into vision itself. The holographic principle, the idea that the entire three-dimensional universe may be written as a two-dimensional code on a cosmic boundary. If the quantum fabric defines the weave, then holography defines the pattern, the way information on the edges gives birth to the depth and structure we see within. In the quiet vastness between galaxies, space appears smooth and continuous, but beneath that apparent calm lies an ocean of quantum agitation. Every point in the void flickers with uncertainty. Virtual particles flash into being and fade away in an instant, their births and deaths balance so precisely that the total energy of the vacuum remains nearly zero. This restlessness is not a defect of nature, it is its most fundamental feature. The quantum fabric never sleeps. Quantum field theory tells us that each type of particle we know, electrons, photons, quarks, is a ripple in an underlying field that fills all of space. Even when no real particles are present, the fields are still there, vibrating faintly, fluctuating according to the strange rules of uncertainty. The energy in these fluctuations is immense, but it cancels almost perfectly, leaving behind what appears to be empty space. And yet, this empty space is the stage from which everything arises. Every region of this fabric shares correlations with its neighbors. When one patch fluctuates upward, another fluctuates downward in a way that keeps the overall balance. These correlations extend outward across immense distances, stitching the universe together with invisible threads. The vacuum, far from being void, is a vast web of relationships, a cosmic sea of entanglement binding every field to every other. To probe these connections, physicists study entanglement entropy. If we imagine dividing the universe into two regions, the amount of information that one region shares with the other measures how entangled they are. When the entanglement is strong, the boundary between them carries a high amount of shared information. When it is weak, the regions become more independent. It turns out that this entanglement entropy is not random, It scales with the area of the boundary that separates the two regions. The geometry of space mirrors the structure of its information. This observation reshaped our understanding of what space actually means. It suggests that geometry is not fundamental, but statistical. The smooth curves we see in the macroscopic world are averages over an unimaginably complex network of quantum connections. In this sense, space-time itself behaves like a collective phenomenon, emerging from the microscopic interplay of entanglement, just as temperature arises from the motion of countless atoms. In the 1990s, studies of black hole entropy revealed the same pattern. The amount of information hidden behind a black hole's horizon was proportional not to its volume, but to its surface area. This was a hint that all of space-time might follow the same rule. The information content of any region of space depends on the area that encloses it, not the volume it contains. This area law of entropy suggests that the fundamental bits of reality live not inside space, but on its boundaries. When researchers applied this insight to the entire universe, the implications were staggering. If space emerges from entanglement, then distance itself is nothing but a measure of how strongly two regions are correlated. Nearby points are highly entangled, sharing large amounts of information. Distant points share less. The fabric of space-time, then, is woven from the gradients of entanglement that run throughout the quantum fields. The more deeply we analyze this picture, the more we see that geometry and entanglement are two expressions of the same structure. The curvature of space corresponds to the way entanglement density varies from place to place. When entanglement increases smoothly, space appears flat. When it changes abruptly, space bends. Gravity, therefore, can be seen as the flow of entanglement, adjusting itself to maintain balance across the network. This idea finds support in calculations from holographic models. In certain configurations, the equations of general relativity emerge naturally from the behavior of entanglement entropy. The geometry of a region is determined by the quantum information shared across its boundaries. The Einstein equations become nothing more than a large-scale approximation of the laws of information flow. Imagine the universe as an intricate tapestry, each thread representing a quantum link between regions of space. Where threads are densely woven, geometry is smooth and strong. Where they loosen, the fabric stretches and curves. The curvature we call gravity is simply the pattern of tension in this weave. The threads are not physical strings but abstract connections, lines of shared information that define the structure of reality itself. It may seem abstract, but this model offers concrete predictions. In regions of high entanglement density, time passes more slowly, just as it does near massive objects in Einstein's theory. In regions of low density, time runs faster. The flow of entanglement across the cosmic fabric defines not only the shape of space, but the rhythm of time. The same relationships that create geometry also generate causality, determining which events can influence which others. This means that time itself could be a side effect of information spreading through the quantum network. As entanglement grows, correlations propagate outward, defining a sequence of before and after. The arrow of time might not point toward entropy increasing, as classical thermodynamics suggests, but toward entanglement spreading. The universe remembers its past because information has flowed from one region to another, embedding correlations that persist. If all of this is true, then the vacuum is not empty. It is alive with computation. Each quantum fluctuation contributes to the ongoing process of encoding, entangling, and rebalancing information. Reality is a vast quantum computer, and the geometry we observe is the visible pattern of its logic. Matter, energy, and even gravity are not separate entities, but emergent expressions of a deeper algorithm at work. The question now is how this algorithm writes space itself. How does the pattern of entanglement create the distances, dimensions, and directions we experience? To answer that, we must look to the holographic principle, where the geometry of the universe is projected from information encoded on its boundaries. In that principle lies the most extraordinary realization yet, that everything within the cosmos, from the smallest atom to the farthest galaxy, may be nothing more than the three-dimensional image of a two-dimensional code written on the cosmic horizon. In every direction we look, the quantum fabric hums with invisible music. The melodies of this song are vibrations of fields, the harmonies are patterns of entanglement, and the rhythm is the flow of information through the structure of space itself. The deeper physicists listen, the more they realize that this symphony does not play within space, it is space. At the smallest scales, the vacuum behaves like a network of infinite complexity. Tiny regions of space-time share entanglement with their neighbors, forming a continuous web of quantum relationships. The strength of those relationships defines what we perceive as distance. Points that are strongly entangled behave as if they are close together, even if they are far apart in ordinary coordinates. If the entanglement between two regions weakens, they drift apart geometrically. Space stretches as information thins. This means that distance is not a fundamental property. It is an illusion born from entanglement strength. Geometry is simply the organization of quantum correlations. To measure distance, we are really measuring how much information one region of the universe shares with another. The concept of near and far emerges only because the quantum network arranges its correlations in a particular pattern. In a sense, space is a story told by information. The tale it tells depends on the density and flow of entanglement. When the story changes, geometry changes. This is why the presence of mass and energy bends space-time. A massive object disturbs the equilibrium of the quantum fabric, altering how information is shared around it. The fabric responds by curving to restore balance, and we perceive that curvature as gravity. The mathematics of entanglement entropy captures this beautifully. The Ryu-Takayanagi relation, one of the crowning achievements of holographic theory, connects the area of a surface in space-time to the amount of entanglement across it. Where information flows freely, the surface expands. Where it becomes constrained, the surface shrinks. Geometry is written in the language of information balance. From this perspective, space-time is not a static arena, but a living entity. It breathes, flexes, and flows as entanglement evolves. Its curvature is not a fixed background, but the outcome of an ongoing negotiation among countless quantum states. Every moment, information flows through the network, shaping the geometry anew. Gravity is the whisper of that flow, the visible echo of the quantum conversations happening everywhere, all at once. If you could see this quantum fabric, it would not resemble the stars and galaxies we know. It would look like a vast lattice of glowing threads, each representing a line of correlation between two regions of the universe. Where threads converge densely, space-time appears smooth and continuous. Where they diverge, space expands and thins. The geometry we inhabit is nothing more than the shape of these connections at an unimaginable scale. This fabric also explains one of the most puzzling facts about the universe: its stability. Classical physics predicts that the vacuum should collapse under its own quantum fluctuations. Yet it remains balanced, neither imploding nor exploding. The reason may lie in the structure of entanglement. The network self-stabilizes because information must always flow in ways that preserve the total balance of correlations. Every quantum fluctuation that disturbs one part of the network is compensated by adjustments elsewhere. The universe maintains itself through the conservation of informational harmony. Even black holes, the most extreme distortions of space-time, follow these same rules. Their boundaries store information according to the area law of entropy. Their gravitational fields are the result of entanglement arranged to its densest possible configuration. When a black hole evaporates, the information it once contained does not vanish. It re-emerges in the form of subtle correlations between the outgoing radiation and the remaining geometry. The fabric of entanglement never loses its data, it only reweaves it. The quantum fabric also helps explain the cosmological expansion of the universe. If geometry is the result of entanglement, then the growth of space corresponds to the spreading of quantum correlations. As time unfolds, regions that were once entangled become less so, and new correlations form in between. The expansion of the universe is the outward ripple of this ever-growing web of information. The cosmos does not expand into anything. It expands as a network of relationships becoming more complex. What emerges from all this is a new kind of physics, one in which the primary ingredient is not matter or energy, but information. The quantum fabric is the ultimate canvas, and everything else is drawn upon it as patterns of correlation. When entanglement changes, geometry changes. When geometry changes, gravity appears. When information flows, time itself moves forward. Perhaps this is why every attempt to unify physics returns to the same central idea. Information is the foundation of reality. The laws of thermodynamics, the mechanics of black holes, the behavior of quantum fields, all speak the same language. Nature does not store its secrets in particles or waves, but in the patterns of how they connect. The story of the universe, then, is not a story of things, but of relationships. The galaxies are not islands floating in a void. They are glowing knots in a vast, invisible web that stretches across the cosmos. The stars, the planets, and even the space between them are different expressions of the same quantum fabric. Gravity, the oldest mystery in science, may be the simplest answer of all, a natural outcome of information finding its most elegant form. As we stand on the edge of this understanding, we begin to see the cosmos not as a machine, but as a conversation. Every particle speaks to every other in the language of entanglement. Every movement, every beam of light, every whisper of gravity is a message sent through the quantum web. To understand that conversation is to glimpse the code from which reality itself is written. And so we arrive at the threshold of the next revelation, the holographic principle. If space is woven from entanglement, then perhaps the entire three-dimensional universe is a projection of a deeper, two-dimensional code. The next chapter will explore how the geometry of gravity, time, and matter may all emerge from the quantum information inscribed upon the boundaries of reality itself. The idea began with a paradox. In the 1970s, when Jacob Bekenstein and Stephen Hawking explored the physics of black holes, they discovered something that made no sense. According to general relativity, a black hole swallows everything that crosses its horizon, hiding it forever from the outside world. Yet quantum mechanics insists that information can never be destroyed. So what happens to the information that falls into a black hole? Does it vanish, violating the laws of physics? Or does it somehow survive? Bekenstein proposed that a black hole has entropy, a measure of the information hidden inside it. Hawking confirmed this with his discovery that black holes emit faint radiation due to quantum effects near the horizon. That meant black holes are not completely black. They slowly evaporate over time. But this led to an even deeper puzzle. If a black hole evaporates away, what happens to the information it contained? If it disappears, quantum mechanics collapses. If it escapes, how can that happen when nothing can cross the horizon outward? The solution, strange as it sounds, came from an idea that changed physics forever. Bekenstein found that the entropy of a black hole is proportional not to its volume, but to the area of its surface. Every bit of information contained within a black hole is stored on its two-dimensional boundary, one tiny unit of area for each bit of information. It was as if the three-dimensional interior of the black hole was a projection, a hologram encoded on its surface. This discovery suggested something profound. Perhaps all of reality works the same way. Maybe every region of space can be described by information encoded on its boundary. This is the essence of the holographic principle, the idea that our three-dimensional universe is a projection of quantum information written on a distant two-dimensional surface. At first, this seemed like pure speculation, but in the late 1990s, Juan Maldacena found a precise mathematical realization of it, now known as the anti-de Sitter and conformal field theory correspondence, or ADS-CFT. In this framework, a universe with gravity in 3 dimensions can be described exactly by a quantum field theory without gravity living on its 2-dimensional boundary. Everything that happens inside, the motion of stars, the bending of light, the flow of time, has a perfect counterpart written on that boundary. The bulk and the boundary are 2 versions of the same reality, like a 3-dimensional movie projected from a 2-dimensional film. In the holographic view, space-time itself is not fundamental. It is emergent. The geometry inside the universe arises from the entanglement structure of quantum information on the boundary. Where information is densely entangled, space curves inward. Where it is sparse, space stretches outward. The entire cosmos becomes a living hologram, with the laws of gravity emerging from the quantum code at its edges. To understand how radical this is, imagine a vast sphere representing the universe. Every event that happens inside, the formation of galaxies, the birth of stars, even your own thoughts, can be described by information inscribed on the surface of that sphere. The 3-dimensional world we experience is like the image inside a holographic crystal, vivid, detailed, and apparently solid, but ultimately an illusion created by the interference of information encoded elsewhere. This does not mean that reality is fake or simulated. It means that geometry is a language written in information. The 3-dimensional universe is not less real because it is a projection. It is real because it emerges from the consistency of that projection. Just as a holographic image feels tangible, though it has no depth, space-time feels solid because its informational code is self-consistent at every scale. In the ADS-CFT correspondence, gravity appears naturally as a consequence of entanglement. When 2 regions of the boundary are highly entangled, their corresponding regions in the bulk are connected by a smooth stretch of space-time. When entanglement decreases, the bulk geometry pinches off, creating curvature, or even separating entirely. This provides a concrete picture of how space-time is woven from quantum information. The smooth geometry of our universe is the large-scale expression of countless microscopic entanglement links. In this framework, black holes become windows into the nature of reality. Their interiors correspond to regions of extreme entanglement on the boundary. The event horizon acts like a screen recording everything that falls in, preserving the information in the form of boundary correlations. As the black hole evaporates, that information slowly leaks back out through subtle changes in the entanglement pattern. What appears as radiation is really information being re-encoded. The universe never forgets. It simply hides its data in geometry. This insight solves the black hole information paradox. Information is never lost. It is preserved in the correlations on the boundary, woven into the holographic code. The same mathematics that describe this process also reproduce Einstein's equations of gravity. In other words, the geometry of space-time and the flow of information are 2 descriptions of the same phenomenon. If the holographic principle applies not only to black holes, but to the universe itself, then we may be living in a cosmic hologram. The vast 3-dimensional expanse we see may be the projection of quantum information encoded on the distant boundary of the cosmos. The cosmic horizon, the limit of what we can observe, could be the ultimate screen, storing the total information of the universe in a 2-dimensional form. This perspective does not diminish the grandeur of existence. It expands it. It suggests that what we experience as space and time are the visible expressions of something deeper, more abstract, and more unified. Matter, gravity, and light are not separate entities, but facets of the same underlying information structure. The universe, in its most fundamental sense, may be a computation unfolding upon the canvas of quantum entanglement. The implications are staggering. If space-time is a holographic projection, then the deepest laws of physics are written not in 3 dimensions, but in 2. The constants we measure, the curvature of the cosmos, even the apparent flow of time could all be consequences of how information is stored and processed on the boundary. The universe may be finite in information content, but infinite in the ways that information can be arranged. What we call reality might therefore be the grandest compression algorithm of all, a perfect holographic code that generates a universe of breathtaking complexity from a surface of pure information. The geometry of space is the shape of that code. The flow of gravity is the execution of its logic. The holographic principle marks a turning point in our understanding of existence. It tells us that we are not separate from the universe's boundary, but part of its projection. Every atom of our being, every moment of our lives is encoded in that grand informational structure. The light that reaches us from distant galaxies carries not just energy, but the whisper of the cosmic code that created them. If this principle is true, then gravity, space-time, and even the sense of distance are illusions born from quantum information woven in patterns too subtle for our senses to perceive. To grasp this truth is to glimpse the deepest unity in physics, the realization that the universe, from the smallest particle to the largest galaxy, is one vast holographic tapestry, its threads made of entanglement, its design written in light. And yet, one mystery remains. If the universe is a hologram, what is the projector? What mechanism transforms the flat code of information into the vivid geometry of space-time we experience? To answer that, we must turn to an even deeper link between two of the most mysterious concepts in physics, entanglement and wormholes. Perhaps, as Juan Maldacena and Leonard Susskind proposed, every entangled pair of particles is connected by a tiny bridge in space-time, an Einstein-Rosen wormhole. If so, then the universe does not merely encode space through entanglement. It connects it literally through the geometry of those connections. In the holographic view, the universe is both a picture and a code. The picture is what we see: galaxies drifting in space, gravity sculpting the shapes of stars, light bending across cosmic distances. The code lies beneath it, an intricate pattern of quantum information written on the cosmic boundary. Every flicker of light, every event in space-time, every thought in a human mind is the unfolding of that code. Yet, if the code defines everything, what links its abstract bits to the geometry we experience as real? The answer may lie in the nature of entanglement itself. When two particles become entangled, their states are no longer independent. Measure one, and the other is instantly defined, no matter how far apart they are. This connection has no physical signal, no exchange of energy, yet it is as real as any bond in nature. Einstein called it spooky, but modern physics sees it as fundamental. In a holographic universe, entanglement is not a curiosity. It is the glue that holds space together. The anti-de Sitter and conformal field theory correspondence revealed that regions of space connected by strong entanglement correspond to regions of smooth geometry in the bulk. Reduce that entanglement, and the geometry pinches or even disconnects. In this way, the very shape of space is controlled by the pattern of quantum correlations. This picture led Juan Maldacena and Leonard Susskind to propose a breathtaking idea. Every entangled pair of particles is connected by a tiny Einstein-Rosen bridge, a wormhole linking their positions in space-time. This conjecture, known as ER equals EPR, unites two of the most mysterious concepts in physics: wormholes, predicted by general relativity, and quantum entanglement, revealed by quantum mechanics. Einstein and Nathan Rosen described wormholes in 1935 as hypothetical tunnels through space-time, while in that same year, Einstein, Boris Podolsky, and Rosen described the paradox of entangled particles. Decades later, Maldacena and Susskind noticed that these two ideas might be the same thing viewed from different scales. If ER equals EPR is true, then entanglement is not merely a statistical link, it is geometry itself. Every pair of entangled particles is connected by a microscopic bridge, too tiny to detect, but collectively, these bridges weave the structure of space-time. The smoothness of space arises from the immense number of such wormholes connecting every quantum state to every other. Where entanglement is strong, the bridges are dense and space appears continuous. Where entanglement fades, the bridges thin and geometry breaks apart. This interpretation transforms our understanding of the universe. It suggests that the flow of gravity, the curvature of space-time, and even the topology of the cosmos are consequences of how these quantum bridges organize. Wormholes are not science fiction tunnels for travel. They are the invisible stitching of reality. Every bit of quantum information shared between two particles translates into a tiny thread of space-time connecting them. If this network of wormholes extends across the universe, then space itself is a vast web of microscopic tunnels, a quantum lattice whose macroscopic shape is the geometry Einstein described. This view dissolves the boundary between relativity and quantum theory. Gravity becomes the collective effect of entanglement geometry, and quantum entanglement becomes the microscopic structure of gravity. The holographic principle provides the mathematical backbone for this picture. In the boundary theory, entangled quantum states correspond to connected regions in the bulk geometry. The more entanglement, the more connected the geometry becomes. When physicists simulate this relationship using tensor networks, they find that the structure of entanglement diagrams reproduces the geometry of spacetime almost exactly. Each connection in the network acts like a wormhole, linking points together in a pattern that defines distance and curvature. Through this lens, even black holes take on new meaning. The interior of a black hole, which appears disconnected from the outside universe, may be connected through entanglement to the radiation it emits. As the black hole evaporates, its interior geometry shrinks while the entanglement with its radiation grows. The information is not lost. It flows through the invisible wormholes connecting inside and outside. The black hole's horizon becomes a dynamic membrane of information flow, balancing geometry and entanglement perfectly. This picture also offers a new understanding of time. The passage of time could be the unfolding of entanglement, the continuous rewiring of connections in the network. As information flows, new wormholes form and old ones fade, reshaping the geometry and defining the arrow of time. The expansion of the universe might be the global growth of entanglement, the stretching of the cosmic web as correlations spread ever farther. If we could somehow look beyond our senses and see the universe as it truly is, perhaps we would not see empty space at all, but a shimmering network of connections, an infinite sea of quantum bridges weaving together every particle, every star, every galaxy. We would see gravity as the gentle flexing of that web, and time as the rhythm of its eternal rearrangement. The holographic universe, then, is not a metaphor, but a map. It shows us how information shapes geometry, how entanglement creates space, and how the cosmos emerges from its own self-entwined code. The boundary of the universe is not a distant wall. It is the source from which reality is projected, a vast quantum screen whose patterns of information define everything within. In this picture, even consciousness fits naturally. Our thoughts, our memories, our perceptions are patterns of information entangled with the physical world. The same quantum principles that shape space and time also shape the architecture of the mind. We are not observers standing outside the hologram. We are part of its projection, self-aware threads in the grand tapestry of entanglement. As we continue this journey, we will see how the flow of quantum information, the constant balancing and rebalancing of entanglement, gives rise to gravity itself. If entanglement is geometry, then gravity may be nothing more than the tendency of information to spread, to equalize, to flow from regions of high correlation to low. The next step is to understand that flow, to see gravity not as a force, but as the movement of information through the quantum network of the cosmos. The holographic vision of the universe changes how we see everything, from the structure of matter to the meaning of space itself. In the traditional picture, space is an arena and matter its actor. But in the holographic view, both stage and actor emerge from the same source, information. Everything that exists inside the universe is a reflection of correlations encoded on its distant boundary. The mathematics of this idea are as beautiful as they are strange. The quantum field theory on the boundary contains no gravity, yet its equations generate the full geometry of a universe that includes gravity. Every fluctuation, every quantum vibration on that boundary surface corresponds to a ripple in the curvature of space within. If you could read the code on that surface with perfect clarity, you would know everything that happens in the three-dimensional world. The motion of planets, the shine of a distant star, the birth of galaxies, all of it would be written in that pattern of information. Physicists have tested this correspondence in countless ways. When they calculate entanglement entropy on the boundary, the result matches the area of minimal surfaces within the bulk geometry. When they simulate the dynamics of black holes in the bulk, the energy flow mirrors the behavior of quantum fields on the boundary. Bit by bit, evidence accumulates that the holographic principle is not merely a metaphor, but a working description of reality. It suggests that what we perceive as space is nothing more than a vast mirage created by entanglement. The more we look, the more consistent the picture becomes. Space-time and quantum information are one and the same. The geometry of the cosmos is the shape of its information. Gravity is the flow of that information. To imagine how this works, consider how a hologram itself is made. A two-dimensional surface is etched with interference patterns of light. When illuminated, these patterns reconstruct a three-dimensional image that appears to float in space. In a similar way, the universe may be a grand hologram in which the two-dimensional quantum information on its boundary projects the illusion of depth and volume we experience. The particles and forces inside are the emergent effects of the interference between countless entangled states. This perspective also offers a profound unity between the smallest and largest scales. The same quantum principles that describe the behavior of subatomic particles govern the geometry of entire galaxies. In the holographic view, scale is an illusion. Whether we speak of a particle or a planet, both are encoded by the same kind of information, written on the same universal boundary. The cosmos is self-similar across every level, its structure repeating in patterns of information that differ only in complexity. Some physicists now speak of reality as a code, a vast computation carried out by the quantum laws of the universe. In this view, every interaction is an operation in that code, every exchange of energy a calculation, every movement a line of logic. The laws of physics are the rules by which information updates itself. When Einstein's equations describe curvature, they are describing how the code adjusts to maintain balance in its flow of information. The holographic principle even explains the precision of physical constants. The speed of light, the strength of gravity, and the fine structure of atomic interactions all arise from how information is distributed in the cosmic code. They are not arbitrary. They are the parameters that keep the holographic projections stable. Change them slightly, and the image of the universe would blur or collapse. Perhaps the most striking implication of the holographic model is its view of causality. In classical physics, cause precedes effect through the passage of time. In the holographic universe, causality arises from the consistency of information across the boundary and bulk. An event occurs not because one thing pushes another, but because the pattern of entanglement demands it. The unfolding of time is simply the logical progression of the code as it computes the next consistent state of reality. This means that time itself may be a form of computation. Each moment arises as the universe updates its information, one step at a time. To us, this appears as the flow of seconds and minutes, but to the cosmos, it is the rhythm of its own processing. When entanglement spreads, time advances. When information flows, geometry evolves. If we could step outside the universe and view its holographic boundary, we might see something astonishing. There, the history of everything that ever happened and will happen would exist at once, encoded in a timeless pattern. From that higher vantage, the flow of time inside the universe would appear as the gradual unfolding of correlations along the boundary. The past, present, and future would all be part of a single cosmic image. This may sound like mysticism, but it is mathematics. The anti-de Sitter and conformal field theory correspondence and its extensions describe exactly such a relationship. Every instant of the universe's evolution corresponds to a rearrangement of entanglement on the boundary. The laws of gravity emerge automatically from this correspondence, as do the thermodynamic laws that govern entropy and temperature. It is as if the universe is not built from particles but from logic, pure relationships crystallized into geometry. From this perspective, consciousness itself becomes a natural extension of the holographic code. The brain is not a detached observer, but a complex pattern of entangled matter interpreting other patterns. When we look at the world, we are reading the holographic projection from within. Our perceptions are local reflections of global correlations, tiny glimpses of the grand computation that writes reality. The holographic principle therefore unifies not only physics, but philosophy. It tells us that what we call here and there, now and then, are not separate realities, but facets of one interconnected structure. The separation between observer and observed dissolves, for both arise from the same network of quantum information. To exist is to participate in that network, to be one thread among countless others in the great tapestry of the cosmos. If we follow this logic further, an even deeper question emerges. If space and time are projections of information, what is the source of that information? What mechanism keeps the holographic code consistent and coherent across all scales? The answer may lie in the geometry of entanglement itself, the way quantum connections literally shape space through microscopic wormholes. In these tiny bridges, where quantum mechanics and gravity meet, we might find the true engine of the universe's holographic projection. The next step is to explore that geometry in detail, to see how the concept of entanglement translates directly into spatial connection. We will dive into the idea that every entangled pair of particles is connected by a wormhole, and that the web of these wormholes forms the scaffolding of space-time. This is the bold proposal known as ER equals EPR, where entanglement and geometry become one and the same, and the very flow of information carves the shape of the universe. The story of gravity has always been a story of connection. In Newton's time, gravity was a mysterious force that reached invisibly across space. Einstein transformed it into the curvature of space-time itself, showing that matter and energy shape the very fabric through which light and motion flow. But the newest vision of gravity goes even deeper. It suggests that the fabric Einstein described is not continuous at all. It is woven from the quantum threads of entanglement. And if those threads can be visualized, each one may look like a bridge through space, a wormhole so small that it lies beyond the reach of any microscope. This is the essence of the ER equals EPR conjecture. The initials come from two papers written in the same year by the same mind. In 1935, Einstein and his collaborator Nathan Rosen proposed what we now call Einstein-Rosen bridges, or wormholes, tunnels that connect two distant points in space-time. In that same year, Einstein, Boris Podolsky, and Rosen described another mystery: pairs of particles that remain correlated even when separated by immense distances, a phenomenon now known as quantum entanglement. The two papers seemed unrelated. One described geometry and gravity. The other described the paradoxes of quantum mechanics. But decades later, physicists began to suspect that they might be two sides of the same reality. Juan Maldacena and Leonard Susskind gave this idea form in the 21st century. They proposed that every pair of entangled particles is connected by a microscopic wormhole. These wormholes are not passages through which matter or light can travel. They are purely geometric manifestations of entanglement. When two particles become entangled, the universe draws a thread between them in the fabric of space-time. Multiply this connection by the countless entangled pairs that fill the cosmos, and space itself emerges as a web of these quantum bridges. In this view, space-time is not simply curved, it is knotted and threaded, alive with invisible links. The more entangled two regions of the universe are, the more connected they become through these geometric bridges. If the entanglement weakens, the bridges stretch and thin until they fade, and the geometry between the regions widens. The smooth continuity of space that we experience is an illusion created by the dense network of these wormholes. The ER equals EPR conjecture resolves several puzzles at once. It explains why entanglement appears non-local without violating relativity. The correlations between entangled particles do not require faster-than-light communication because the particles are not truly separate. They are connected through the geometry of space-time itself. The instantaneous coordination between them is simply the reflection of their shared bridge. There is no message being sent, only the revelation of a deeper unity. It also offers a new way to think about black holes. Imagine two entangled black holes, separated by light years. According to ER equals EPR, they are connected by a wormhole. Anything that falls into one could, in theory, emerge from the other, not as a form of travel, but as a continuation of information flow through the entanglement that links them. The interior of a black hole, which seems hidden from the outside world, may actually be a region of the same geometry that connects it to the rest of the universe through entanglement. The event horizon becomes not a wall, but a membrane of communication within the quantum fabric. This concept bridges the gap between gravity and quantum mechanics. For the first time, it provides a geometric interpretation of entanglement and a quantum foundation for geometry. It tells us that space is not a static stage, but a living network of connections, where gravity is the macroscopic echo of countless microscopic wormholes weaving together every point of the cosmos. Physicists have simulated aspects of this idea using quantum computers. By constructing systems of qubits whose entanglement patterns mimic those of theoretical wormholes, researchers have observed behavior that matches the mathematics of gravity in miniature. In these experiments, information sent into one side of an entangled system reappears on the other, just as it would through a wormhole. Though no matter actually travels between them, the structure of their entanglement reproduces the essential geometry of spacetime. To imagine this more intuitively, think of spacetime as a vast three-dimensional web of glowing threads. Each thread represents entanglement connecting 2 points. Some threads are short and bright, linking nearby regions. Others stretch across cosmic distances, faint but unbroken. The density of these threads determines the shape of space. Where the web is tightly woven, space curves smoothly, and gravity is strong. Where it is sparse, space stretches outward and gravity weakens. Each node in this network is a particle, and each connection is a quantum bridge, an ER equals EPR link holding the universe together. From this picture, gravity emerges naturally. When matter gathers in one region, the local network of entanglement tightens. The increased density of connections curves the surrounding geometry, drawing nearby matter inward. What we perceive as gravitational attraction is simply the geometry of these quantum links, adjusting to maintain balance in the network. The same principle applies to the expansion of the universe. As entanglement spreads and new connections form, the geometry stretches, increasing the apparent distance between distant regions. The cosmic expansion is not matter flying through space, it is the network itself growing, its geometry reweaving as correlations evolve. The ER equals EPR conjecture also offers insight into the black hole information paradox. In the holographic framework, the information inside a black hole is encoded in the entanglement between the black hole and its emitted radiation. The interior and the exterior are connected by wormholes, so information never truly disappears. It merely flows through the geometry of entanglement, ensuring that quantum mechanics remains consistent. This model even suggests that the universe itself may be a single, vast wormhole network, where every particle is linked to every other by entanglement. The whole of existence would then be a single connected system, an unbroken fabric of information from which space, time, and gravity all arise. We see separations only because we cannot perceive the full pattern. If ER equals EPR is true, then the phrase space-time fabric becomes more literal than metaphorical. The threads are real, though invisible. They are the wormholes of entanglement, the connections that give space its texture and time its flow. Every interaction, every exchange of energy, every act of observation rewires these threads, reshaping the geometry of the cosmos. In this way, reality becomes both simpler and stranger. Simpler because it unites the laws of gravity and quantum mechanics under one principle: connection. Stranger because it tells us that space is not empty, that separation is an illusion, and that every particle in the universe is silently linked to every other through the unseen geometry of entanglement. To truly grasp this vision, we must look at gravity not as a force that acts upon space, but as the very flow of information through this quantum network. The curvature of space-time is not something imposed. It is the consequence of how entanglement changes. When information flows, space bends. When information balances, space relaxes. Gravity, in its purest form, is the music of entanglement arranging itself into harmony. The next step in our journey is to listen to that music, to explore how the flow of quantum information, the continual balancing of entanglement, gives rise to the force we call gravity. If space-time is woven from wormholes and entanglement, then gravity may be the rhythm of that weave, the gentle pulse of the universe seeking equilibrium in its eternal conversation of information. In the deepest quiet of the universe, beneath the glitter of galaxies and the whisper of cosmic radiation, an invisible web stretches across everything. It is not a web of matter or light, but of pure relation, of quantum entanglement, threading together regions of space that may be separated by billions of light years. This web does not live within space. It is space. The ER equals EPR conjecture tells us that what we experience as geometry is nothing more than the shape of this cosmic web, and what we experience as gravity is the flow of its connections adjusting, tightening, and relaxing over time. If we could see this web directly, we would witness a spectacle unlike anything imagined by science fiction. Between every particle, a filament of correlation hums with invisible tension. When two particles become entangled, a tiny Einstein-Rosen bridge forms between them, so minute that its length is smaller than any measurable distance, yet real in the geometry of quantum gravity. Each of these wormholes is not a tunnel through which matter can travel, but a path through the abstract geometry of information. Together, they create the smooth continuum we call space-time. The strength of these bridges determines the curvature of the geometry they form. When entanglement increases between two regions, the bridges shorten and the regions draw closer in geometric terms. When entanglement decreases, the bridges lengthen or fade, stretching space between them. This is what we perceive as gravitational curvature. Massive bodies, filled with dense quantum fields, create more entanglement around them. The network tightens, pulling nearby regions inward. Space itself bends because information prefers to remain balanced. To describe this balance mathematically, physicists use the language of entanglement entropy. In holographic models, the area of a minimal surface in space-time corresponds exactly to the amount of entanglement across that surface. When the pattern of entanglement changes, so does the geometry. Einstein's field equations emerge from this correspondence, describing how curvature responds to the flow of energy and information. The geometry we live in is thus the large-scale shadow of an information network seeking equilibrium. Imagine tossing a stone into a still pond. Ripples spread outward, carrying energy through the water. In space-time, those ripples are gravitational waves, the echoes of shifting entanglement. When two black holes merge, their internal entanglement networks reorganize violently, sending ripples through the surrounding geometry. What our detectors record as the trembling of space itself is the vibration of quantum connections finding a new balance. Gravity is not a mysterious pull, it is the dynamic flow of information within the cosmic fabric. This flow also explains why gravity is universal. Every particle, regardless of charge or composition, participates in the entanglement network. Unlike the electromagnetic or nuclear forces, which act only on specific kinds of matter, gravity arises from the geometry shared by all information. It is the collective behavior of the entire quantum web. When we feel the pull of Earth, we are not being acted upon by a separate force, but are following the natural curves of information flow through space-time. In this framework, distance and time lose their classical meaning. They are not fundamental quantities but emergent ones, derived from how information is connected. Two particles that appear light years apart may in fact be close neighbors in the entanglement network, joined by a microscopic wormhole. Conversely, points that seem adjacent in space might be far apart in information terms. The geometry we perceive is a projection of the far richer geometry of entanglement. Such a view carries profound implications for cosmology. Consider the Big Bang, the supposed origin of all space and time. If space-time arises from entanglement, then the early universe was not a tiny, dense point of matter, but a state of near-perfect correlation, a single web with minimal differentiation. As it evolved, new degrees of freedom became entangled, and geometry expanded. The expansion of the universe may thus be nothing more than the spreading of quantum connectivity, the continual knitting of new bridges as information flows outward. The same principle can describe the universe's eventual fate. If entanglement ever stops spreading, the geometry would cease expanding. If it continues indefinitely, space will stretch forever. The destiny of the cosmos is tied to the dynamics of information, not to the push of an external force. The ER equals EPR framework also transforms our understanding of black holes. Inside the horizon, time and space trade roles, and the geometry seems to end. But in the language of entanglement, nothing ends. The interior of a black hole is entangled with the universe outside, connected through wormholes that preserve information, even as matter falls inward. When the black hole evaporates through Hawking radiation, the information does not vanish. It migrates through those quantum bridges, re-emerging in the correlations of the radiation itself. The universe, in its geometry, remembers everything. Some theorists have extended this picture even further, suggesting that all of spacetime may be a single connected wormhole, a global ER equals EPR structure encompassing the entire cosmos. In this view, every point is joined to every other through an unimaginably dense network of microscopic bridges. Separation is an illusion born from the limits of our perception. The unity of the cosmos is not philosophical poetry. It is a geometric fact. If we could magnify this structure to human scales, it would resemble a living organism, with information flowing like blood through its veins of entanglement. Energy moves, geometry bends, and the web hums with constant exchange. Gravity is its heartbeat, the rhythmic adjustment of the network as it balances the flow of correlations. This concept brings us close to an even deeper truth. The distinction between geometry and information is artificial. They are not two separate aspects of reality, but two languages describing the same phenomenon. When we speak of curved space, we are describing how information arranges itself. When we speak of entanglement, we are describing how geometry connects itself. The universe is both map and territory, code and manifestation, thought and form. And yet, this unity raises one final question. What governs the flow of information through the network? What law determines how entanglement evolves, how wormholes stretch or contract, how geometry breathes? The answer may lie in the principle of entropy, the universal tendency of systems to spread information evenly, to seek balance. If gravity is the manifestation of this flow, then perhaps it is not a fundamental force at all, but an emergent consequence of information striving for equilibrium. The next chapter will explore this possibility in depth. We will see how gravity might arise from the statistical behavior of information itself, how the movement of entanglement across regions of space-time can create the sensation of attraction, and how the universe's geometry could simply be the large-scale reflection of information flowing toward balance. The flow of information defines everything. Gravity, in this vision, is not a force acting across a void. It is the behavior of the void itself when information moves. Each thread of entanglement carries a faint pulse, a constant tendency to balance the distribution of knowledge across the cosmos. These pulses are not mechanical. They are statistical, born from the logic that governs how information spreads in quantum systems. When information is concentrated, it flows outward, creating curvature. When it is evenly distributed, geometry flattens. This movement of information is what we perceive as gravity. A massive object, like a planet or a star, is not truly a clump of matter. It is a region where quantum information is densely stored, where entanglement is thickest. The surrounding space reacts to this concentration by reshaping itself, curving so that the flow of information remains smooth. When you drop an apple, it does not fall because a force pulls it. It follows the natural gradient of entanglement, sliding through the geometry that information itself has sculpted. The Dutch physicist Erik Verlinde took this idea and gave it a name: entropic gravity. He argued that gravity arises from changes in the amount of information, or entropy, associated with the positions of matter. When information is rearranged, the system feels a statistical push toward equilibrium. This push is what we interpret as gravitational attraction. Just as heat flows from hot to cold, information flows from concentrated to diffuse, and that flow curves space-time. In a sense, gravity is a mirage of information equilibrium. It is not fundamental, but emergent, much like temperature or pressure. No single atom has a temperature, yet the collective motion of many atoms creates it. Likewise, no single quantum state possesses gravity, but together, their entanglement weaves a geometry that behaves as if there were a force at play. If this picture is correct, the laws of motion become expressions of information flow. A freely falling object follows the most efficient path through the informational landscape, a path of constant entropy, a geodesic in the geometry of knowledge. The curvature of that geometry determines acceleration, and acceleration changes the rate at which information flows. Einstein's equations, which once described the shape of spacetime, now reveal themselves as the equations of informational balance. This interpretation illuminates some of the universe's deepest puzzles. The mysterious dark energy that drives cosmic expansion could be the manifestation of information spreading across the cosmic horizon. As the universe grows, new regions become entangled, and the expansion continues. Similarly, what we call dark matter, the invisible mass shaping galaxies, may be a correction arising from the way information organizes itself in complex systems. Instead of unseen particles, it could be the statistical footprint of entanglement geometry. The elegance of this view lies in its unity. Gravity, thermodynamics, and quantum theory are not separate domains, but facets of one law: the conservation and flow of information. The universe does not merely evolve, it computes. Every physical process, from the orbit of planets to the flicker of subatomic particles, is a step in that computation. The code is written in the logic of entanglement, and gravity is the program's emergent behavior. To grasp this intuitively, picture the universe as a vast ocean of data. Matter and energy are waves on its surface, rising and falling as information redistributes itself. Where the waves are tall and steep, geometry curves. Where they are calm and wide, space flattens. Gravity is the tendency of these waves to smooth themselves out, to spread the information they carry evenly across the sea. Even the passage of time can be seen through this lens. Time flows because information flows. The arrow of time is not dictated by the ticking of clocks, but by the continual increase of entanglement. Each moment adds new correlations to the network. deepening the fabric of reality. The universe remembers its past, not through static records, but through the evolving web of entanglement that stores every interaction. Seen this way, the entire cosmos behaves like a self-correcting quantum computer, maintaining the consistency of its code through the flow of information. Gravity, instead of being an external law, becomes the internal logic of that computation, the rule that keeps the program coherent. When a star collapses into a black hole, it is not vanishing from reality. It is compressing information to its densest possible form, encoding it on the boundary of space as pure geometry. This unification of entanglement, geometry, and information marks a new stage in humanity's understanding of the universe. We have moved from seeing gravity as a mysterious force to understanding it as curvature, and now perhaps to recognizing it as the flow of information itself. The dance of galaxies, the shimmer of light, the bending of space, all are expressions of a single principle. The universe is an ocean of entanglement, forever rearranging its own connections to preserve harmony. The next step in our exploration is to see how this harmony becomes structure, to understand how the density and arrangement of entanglement define the very shape of space. If information flow creates curvature, then the geometry of the universe must be the visible trace of that process. In the next chapter, we will follow those traces into the mathematics of tensor networks and discover how information literally becomes geometry, how space-time is drawn from quantum data, pixel by pixel, connection by connection, until the illusion of reality becomes complete. Gravity has always seemed inevitable. From the fall of an apple to the orbit of a moon, it governs motion with silent authority. Yet beneath its familiarity lies a deeper truth. Gravity is not a force at all. It is the whisper of information flowing through the fabric of reality. Every curvature of space, every rhythm of time, every dance of celestial bodies arises from the tendency of information to move, to balance, to spread. To see this clearly, we must forget the notion of space as emptiness and think, instead of it, as a living ocean of quantum information. Each region of this ocean holds entanglement with its neighbors, forming an invisible web that defines geometry itself. When this web is disturbed, when information becomes unevenly distributed, it begins to flow. This flow creates what we experience as gravity. Matter does not bend space through mass. It reshapes the pattern of information, and space bends in response. Eric Verlinde, building upon the ideas of Jacob Bekenstein and Stephen Hawking, proposed that gravity emerges from changes in information entropy. When a particle moves, the amount of information that the universe possesses about its position changes. The system, seeking balance, adjusts. The result is a statistical push, not unlike the way air moves from high pressure to low. Gravity is the same phenomenon, translated into the language of quantum information, the tendency of reality to even out its knowledge of itself. This idea, known as entropic gravity, gives a startlingly simple picture of the universe. Consider a holographic screen, an imaginary surface encoding the information about everything within a region of space. The number of bits stored on this surface grows with its area, not its volume. When a particle approaches the screen, it changes the amount of information needed to describe the system. The resulting shift in entropy generates a force, a statistical urge toward equilibrium. That urge is gravity. In this way, gravity becomes not a fundamental interaction, but an emergent behavior, like temperature or pressure. Just as temperature arises from the average motion of countless molecules, gravity arises from the collective behavior of countless entangled quantum states. The curvature of space-time is the geometry of their balance. When information flows smoothly, space is flat. When it pools unevenly, space curves. What we call a gravitational field is nothing more than the map of that informational gradient. This reimagining unites gravity with thermodynamics and quantum mechanics. Entropy, once the measure of disorder, now becomes the measure of structure itself. A black hole's horizon, for example, contains the maximum possible entropy for its area, the densest encoding of information permitted by nature. When a black hole grows, its surface area increases, representing the influx of new information. The Hawking radiation that leaks away carries that information back out, maintaining the balance. The black hole is not an abyss, but a perfect processor, transforming geometry into data and data back into geometry. At every scale, the same principle holds. From galaxies to subatomic particles, gravity reflects the universal tendency of information to flow toward equilibrium. When two bodies attract, it is because the network of entanglement between them is adjusting to minimize informational tension. Their motion is not dictated by mysterious forces pulling through the void, but by the geometry of data seeking harmony. The orbits of planets, the collapse of stars, the formation of clusters, all are ripples in the grand current of entanglement. This view also explains the cosmic expansion. As information spreads across the universe, new regions of entanglement form, and geometry stretches to accommodate them. The accelerating expansion we attribute to dark energy could be the natural result of this process, a manifestation of the universe's continual drive to distribute information evenly across its horizon. Space does not expand into nothing. It expands as new connections emerge, rewriting the structure of the quantum fabric. Even time itself may arise from this flow. In classical physics, time is an external dimension through which events pass. In the informational universe, time is the measure of change in entanglement. Each moment corresponds to a new configuration of quantum relationships. The arrow of time points in the direction of increasing entropy, the universe's memory of its own evolution. We experience time's passage because information is never static. It perpetually spreads, weaving new threads into the fabric of reality. If this is true, then Einstein's equations are not fundamental laws, but statistical averages. They describe how geometry responds to the movement of information on large scales, much as the laws of fluid dynamics describe the behavior of countless water molecules. Deep beneath those smooth equations lies a microscopic world of quantum data, entangling, disentangling, and rebalancing, giving rise to the curvature we perceive as gravity. At the heart of this idea lies an elegant symmetry. The more information a region contains, the more curved its geometry becomes. The more curved the geometry, the slower information flows. Gravity thus regulates the tempo of the universe's computation, ensuring that information never moves faster than the speed of light, the ultimate limit written into the code of reality. This vision of gravity as information flow also provides a bridge between the holographic principle and the ER equals EPR framework. In the holographic picture, all information is encoded on a boundary. In the ER equals EPR model, entanglement connects regions through wormholes. Entropic gravity unites both by showing that the flow of information across those connections generates curvature. The bending of space is the physical echo of information traversing the cosmic web. Imagine space as a network of countless nodes, each carrying a fragment of information. When data moves from one node to another, the network rearranges its connections. Locally, that rearrangement appears as motion, as attraction, as force. The apple falling to earth is not pulled by invisible hands. It is following the shortest informational path through a geometry that has adjusted to the distribution of knowledge in the system. This interpretation also resolves one of the strangest puzzles in physics: the weakness of gravity compared to other forces. Electromagnetism and the nuclear interactions operate directly on quantum states, while gravity emerges only from their collective statistics. It is a second-order effect, arising from the vast averaging of informational behavior. Its universality and weakness are natural consequences of its origin, as an emergent, not fundamental, phenomenon. Through this lens, the cosmos becomes a living network of computation. Every atom, every star, every black hole participates in the great balancing of information. Gravity is the visible form of that balancing, the smooth rhythm of the universe correcting its own asymmetries. It is the geometry of knowledge in motion. To understand this fully is to see that nothing truly falls. Information flows and geometry follows. Every orbit, every collapse, every expansion is the reshaping of the web of entanglement. The universe does not obey gravity. It is gravity, endlessly adjusting, endlessly computing, endlessly finding harmony in its own code. And if gravity is the flow of information, then perhaps space itself is nothing but a map of that flow, drawn by the density of connections between quantum states. The next revelation lies in the realization that geometry does not merely emerge from information. It is information, arranged in a precise mathematical pattern. In that pattern, the entire cosmos takes form, its shape determined by the logic of entanglement itself. Every shape in the universe, from the curve of a galaxy to the smooth arc of a light wave, may arise from the same hidden principle, the arrangement of quantum information. When we look deeply into space-time, we find that geometry itself is not fundamental. It is born from the pattern of entanglement, the intricate web of correlations that link every quantum field to every other. The universe is not built from matter or energy, but from structure, an infinite lattice of information giving rise to the illusion of space. This insight was first made tangible through the idea of tensor networks. In this mathematical framework, each quantum state is represented as a node, and each entanglement as a line connecting two nodes. Together, they form a web whose shape defines geometry. When the entanglement is dense, the network folds inward, forming regions of strong curvature, like those near massive stars. When it is sparse, the network stretches, creating the flat expanses between galaxies. The shape of space is therefore the direct image of how information is shared. Mark van Ramsdonk was among the first to propose that the smoothness of space-time depends entirely on quantum entanglement. In his thought experiments, he showed that if one were to gradually reduce the entanglement between two halves of a quantum system, the corresponding regions of space-time would drift apart. Remove the entanglement entirely, and the space itself would split in two, disconnecting like severed cloth. This was more than mathematics, it was a revelation. Without entanglement, there is no geometry, no continuity, no universe. In this picture, what we call distance is simply a measure of how much two regions of the universe are entangled. Nearby points in space share large amounts of information. Distant points share very little. The curvature of space-time emerges naturally from the way these correlations are distributed. Space bends because entanglement is not uniform. It clusters, flows, and rearranges, sculpting the geometry we inhabit. The tensor network model visualizes this beautifully. Imagine an enormous, branching web stretching outward from a central point, each node connected to several others, in a pattern that grows like a tree. This is a holographic map of a universe. The outer edges represent the quantum fields living on the boundary, the fundamental bits of information. The interior geometry arises from how these bits are connected. The deeper you move inward through the web, the more coarse-grained the information becomes, and the more curved the geometry appears. The shape of space-time is the result of information compression. This model, known as a multi-scale entanglement renormalization. Ansatz, or mirror, is not just a clever metaphor. It reproduces key features of general relativity. The shortest paths through the network correspond to geodesics, the same paths that light follows in curved space. Entropy in the network's links corresponds to the area of surfaces in the emergent geometry. The equations of Einstein's theory emerge naturally from the balance of entanglement across the structure. What Einstein described as curvature is, in this deeper view, the statistical pattern of quantum data. The implications are profound. Every atom, every planet, every galaxy, is a localized expression of a much larger informational geometry. Matter and energy are not ingredients of space. They are configurations within it, knots in the network of entanglement. The gravitational field is not something acting upon this network, but the network itself adjusting its internal logic. When matter moves, information rearranges and geometry flows with it. This vision dissolves the boundary between physics and computation. The universe behaves like an enormous self-correcting algorithm, its geometry determined by the efficiency with which it processes and distributes information. Entanglement acts as a stabilizer, keeping the geometry coherent even in the presence of local fluctuations. If too much information concentrates in one region, curvature increases and the network rebalances by spreading correlations outward. This dynamic equilibrium is what we perceive as the smooth, continuous nature of space. Even the stability of black holes can be understood this way. A black hole's interior is a region where entanglement density reaches its limit. Its horizon marks the boundary beyond which the network becomes so tightly woven that no new information can pass inward. The Bekenstein-Hawking entropy formula, which relates the area of the horizon to the amount of information it contains, fits perfectly into this framework. The surface area of the black hole is the measure of how many quantum connections terminate there, the number of threads in the cosmic web that define its geometry. If one were to zoom out from this microscopic picture, the universe would appear as a single seamless tapestry. But zoom in far enough, and that continuity dissolves into nodes and connections. Just as a high-resolution image is made of pixels, space-time is made of bits of information, each linked to others by entanglement. The Planck scale, the smallest possible unit of length, is where this structure becomes apparent. Below that scale, geometry ceases to have meaning. There is no distance, no direction, only information and its relationships. This view carries a quiet but radical consequence. Space is not a container, and time is not a river. Both are emergent languages that describe how information arranges itself. They are conveniences for beings like us, whose minds interpret the flow of entanglement as motion and change. The universe does not exist in space and time. It creates them as it computes. If we could step outside this computation, we might see reality as a vast network of lightless connections, pulsing with quantum logic. Every particle, every wave, every moment would be a node in that network. The geometry we see would be a projection of its structure, and the laws of physics would be the syntax of its code. In this sense, gravity is the grammar of the universe, the rule by which information arranges itself into coherent form. The most astonishing realization is that the same mathematics used to protect quantum information in computers, known as quantum error correction, also describes how space-time preserves its stability. In a quantum computer, entangled qubits share information redundantly so that if one is disturbed, the system can recover the lost data. The universe seems to do the same. Regions of space-time are entangled redundantly with others, ensuring that local disruptions do not destroy the global geometry. Space corrects itself the way a code repairs errors. This means that the laws of physics are, at their core, laws of information integrity. The constants of nature, from the speed of light to the strength of gravity, are not arbitrary numbers, but parameters that ensure the universe's code remains stable. They are the rules that keep the holographic projection from glitching. The cosmos does not merely compute, it protects its own computation. In this light, gravity and geometry are not separate entities, but two expressions of the same truth. Gravity describes how information flows. Geometry describes the path that flow takes. When entanglement thickens, space curves. When it relaxes, space straightens. Every movement of matter, every photon of light, every tick of time is a manifestation of information reshaping itself. Reality, then, is not made of things, but of relationships. The universe is a network that exists because it is connected, and its connections are its only substance. Geometry is the poetry of those connections written in space-time, and gravity is the rhythm that gives that poetry its music. If we accept this, the final step becomes clear. The ultimate laws of the universe are not about mass or motion, but about information and balance. The cosmos is not governed by forces, but by logic, an eternal conversation between bits of quantum data. The next step is to see whether we can observe this conversation directly, to test whether gravity truly emerges from information. For that, we must look not to the heavens, but into the laboratories where physicists are beginning to simulate the universe itself. If gravity is not a fundamental force but the result of information flow, then there must be ways to test it. The challenge is that this kind of gravity does not act through mass and motion alone. It emerges from quantum relationships. To confirm this, we must look where quantum mechanics and general relativity meet, in the smallest scales, the hottest energies, and the strangest experiments. The first hints come from black holes. Stephen Hawking's discovery that they radiate energy was the first sign that gravity and quantum mechanics are inseparable. When a black hole emits Hawking radiation, information encoded on its surface escapes slowly into the universe. The Bekenstein-Hawking formula links the surface area of a black hole to its entropy, proving that geometry carries information. Every tiny change in the event horizon corresponds to a shift in the balance of entanglement. This is not a coincidence. It is evidence that space-time obeys informational rules. The holographic principle, tested through the anti-de Sitter and conformal field theory correspondence, strengthens that claim. By calculating properties of quantum systems on a flat boundary, physicists can reproduce the behavior of gravity inside a curved space. This correspondence has been verified through countless simulations. When researchers compute energy flows in a boundary field theory, the results mirror gravitational waves in the bulk. Each confirmation hints that gravity and entanglement are truly two faces of one reality. The most direct attempts to detect emergent gravity come from laboratory experiments. In 2017, Sugata Bose and Chiara Marletto proposed a method to test whether gravity itself can cause quantum entanglement. If two tiny masses are placed close enough, their mutual gravitational field should entangle them, if gravity is quantum in nature. If not, they will remain uncorrelated. Several groups around the world are now refining instruments sensitive enough to perform this test. The outcome will not only reveal whether gravity is quantum, but whether it is indeed a manifestation of entanglement. Quantum computers also offer a new path. By constructing entangled qubit networks that mimic the holographic structure of space-time, scientists have already recreated simplified versions of wormholes in the lab. In 2022, a collaboration between Google and Caltech simulated a tiny wormhole using a chain of quantum bits. The data sent through one end reappeared on the other, echoing the behavior predicted by the ER equals EPR framework. Though no actual tunnel formed, the informational geometry behaved as if it had. These results are still modest, but they suggest that gravity's origin can be studied not by observing stars, but by engineering entanglement. The universe's deepest mysteries might be decoded not through telescopes, but through algorithms. The key is to treat geometry as computation. If we can program the Faraday entanglement structure, we can shape simulated spacetime. In this way, the laboratory becomes a miniature cosmos. The black hole information paradox, long thought unsolvable, also finds new clarity through these ideas. The paradox asks whether information falling into a black hole is destroyed or preserved. In the entanglement picture, nothing is ever lost. Information flows through the geometry of wormholes and re-emerges in the radiation. Experiments in quantum simulation are now reproducing this effect, showing how information can be scrambled and later recovered, just as holographic gravity predicts. Though we cannot yet peer into Planck-scale geometry, we can already see the fingerprints of informational gravity everywhere, from the thermal behavior of black holes to the limits of quantum computation. Each discovery brings us closer to the moment when we can say with confidence that space-time is not a thing, but a process, not a stage, but a script continually being written in the language of information. The next step in this unfolding story is to follow that script to its logical end, to ask what the universe truly computes, and what kind of code could give rise to everything from electrons to galaxies. If gravity is information in motion, then reality itself may be the program, and existence the act of computation. The closer we look at reality, the more it resembles computation. Every interaction, every exchange of energy, every flicker of light can be described as an operation in an immense quantum program. If gravity emerges from the flow of information, then the universe itself is not merely governed by mathematics, it is mathematics in motion. The cosmos is a processor, and its architecture is written in the geometry of entanglement. Black holes reveal this truth most clearly. They are not monsters of destruction, but perfect data storage systems. When matter and energy fall in, they do not vanish. They are encoded on the event horizon as quantum information. The entropy of a black hole, proportional to the area of its surface, measures how many bits of data it contains. As it radiates energy through Hawking radiation, those bits leak back out, rearranged but preserved. The process is slow, deliberate, and exact, as if nature itself refuses to lose even a single bit of its own memory. This precision led physicists to a profound realization. The same mathematical principles that govern quantum error correction, the methods used to protect fragile qubits in quantum computers, also describe the stability of space-time. In both systems, information is redundantly encoded so that local errors do not destroy the whole structure. In a quantum computer, this ensures accurate computation. In the universe, it ensures that space remains coherent even when disturbed by violent events like supernova or black hole collisions. The holographic correspondence shows how this works. The boundary of the universe acts like a code that continuously checks and restores the data defining the interior. If part of the bulk geometry is perturbed, the information is still recoverable from the boundary's entangled state. This redundancy explains why space-time is so stable. It is protected by the same logic that guards quantum information. Reality is its own correction code. Seen this way, the laws of physics are the rules of a universal computation. The constants of nature, such as the speed of light and the strength of gravity, are not arbitrary values, but parameters that ensure the stability of the code. They define the balance between information flow and coherence. Change them, and the program fails. Space unravels, time fractures, and causality dissolves. The universe exists because its code is perfectly tuned for self-consistency. Some physicists now suspect that the cosmos may even operate like a quantum error-correcting code in its entirety. Each region of space holds information redundantly stored in other regions, making the universe both resilient and self-aware. In this interpretation, reality is not computed from the top down, but from within. Every particle and every field performs its part of the calculation. The universe is the sum of all its self-checking interactions. This picture also bridges physics and consciousness. The brain, too, processes information through patterns of correlation, forming networks not unlike the entanglement webs that shape space-time. Perhaps thought and geometry are two expressions of the same universal behavior, the flow of information organizing itself into coherent form. When we think, we are performing the same operation the cosmos performs at every scale, the transformation of entropy into structure. If that is true, then our awareness is not separate from the code of the cosmos, but a reflection of it. We are subsystems of the grand computation, briefly self-referential nodes within its infinite logic. The act of observation is the universe reading its own data, and the laws of physics are the syntax through which it understands itself. In this vision, gravity becomes the organizing principle of cosmic computation. It is not a force, not even a field, but the flow of information that maintains the coherence of reality's code. It keeps the universe stable, consistent, and readable. Every falling apple, every orbiting moon, every bending of light is a checksum in the great program of existence. The universe does not run on laws. It is the law, continuously executing its own code. Black holes are the memory drives. Wormholes are the logic gates. Entanglement is the circuitry. Gravity is the software that keeps it all synchronized. Matter, energy, and space-time are simply the visible manifestations of that invisible computation. If we could see this cosmic machine as a whole, we might recognize its perfection. It neither starts nor stops. It evolves in cycles of computation, eternally rewriting itself. And within this system, everything is preserved. Every event, every thought, every fluctuation encoded somewhere in the quantum web. The universe, in its deepest truth, is information remembering itself. The next chapter will bring this vision to its conclusion. If gravity, geometry, and computation are all aspects of the same phenomenon, then the cosmos itself is a single woven entity, a tapestry of entanglement whose threads are time, space, and thought intertwined. Everything we have learned points to a single truth. The universe is not made of matter, but of relationships. Gravity, space, and time are the language through which information speaks itself into existence. Every atom, every star, every living being is a note in a vast symphony of entanglement, each vibration resonating through the geometry of reality. Einstein gave us the melody when he showed that gravity is the curvature of space-time. Quantum theory revealed the harmony when it uncovered entanglement, those invisible threads that bind particles together beyond distance. Now, modern physics suggests that these two are not separate instruments, but the same composition played in different octaves. The curvature Einstein described may simply be the geometry drawn by the flow of entanglement. In this picture, the cosmos is a tapestry woven from information. The threads are quantum connections, the patterns are geometry, and the texture is gravity itself. The denser the weave, the more curved the fabric. The sparser the weave, the more open the space. What we call time is the continual act of weaving, the universe updating its own pattern, moment by moment, in the ongoing computation of existence. Each of us, too, is part of that computation. The particles in our bodies are connected to the stars through ancient threads of entanglement. The warmth of sunlight, the pull of the earth, the flow of breath. These are expressions of the same universal code, written in countless forms but unified by logic. Consciousness, then, may be the reflection of the cosmos becoming aware of its own network, an echo of the information that sustains reality itself. The story of gravity is the story of unity. It began as a mystery of falling apples and curved orbits, and ends as an understanding that nothing truly falls. Information simply flows. The universe bends not under weight, but under thought. Not through force, but through balance. The geometry of space-time is the shape that information takes when it organizes itself into meaning. Perhaps this is the ultimate revelation. The cosmos is not a collection of objects, but a single living pattern, a self-reflective web of entanglement where the laws of physics are the rules of conversation between its threads. To exist is to participate in that dialogue, to be a node through which information passes, shaping and reshaping the infinite fabric. Gravity is not a force that pulls. It is the shape drawn by quantum relationships, the silent flow of entanglement giving rise to space, time, and the story of everything.